Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about a problem. So the problem is given as you are given a number and you have to find if a given number is prime or not. Before we move on, let's understand what is meant by prime numbers. A number is said to be prime if it has only two divisors, a number itself or one. Let's see with an example. Here we have 7 as a number and 7 has exactly two divisors, that is 1 and 7. That's why 7 is a prime number. Next is 13. 13 also has two divisors, 1 and 13. That is why 13 is also a prime number. In case of 4, 4 has divisors like 1, 2 and 4 itself. So it has more than two divisors. That's why 4 is not a prime number. In case of 10, 10 has divisors 1, 2, 5 and 10. It has 4 divisors. It means it is also not a prime number. So let's pause this video for a while and think about a solution to solve this problem. Okay, now let's see the first implementation to solve this problem. So we have a function is prime and this function is expecting n from us. In this function, we are simply checking if n is equal to 1, then return false. Why we are doing this? Because 1 is neither a prime number nor a composite number. That's why we are simply returning false if n is equal to 1. And after that, we are simply running a loop from 2 to less than n. And in each iteration, we are checking if n is divisible by I or not. If it is divisible, then we immediately return false. And once the for loop gets completed, we simply return true. Means we are not able to find any divisor of this number. It means it is a prime number. So basically, we are searching a number from 2 to n, and in each iteration, we are dividing our number with that number. And if we found any divisor, then we simply declare that okay, we found the divisor. It means it is not a prime number. So let's see with an example. Let's say if we pass n is equal to 7, then this loop runs from 2 to 6. Because when I equals to 2, 7 is not divisible by 2. When I becomes 3, 7 is not divisible by 3, and so on and so forth. So at the last, this piece of code returns true. It means 7 is a prime number. In case of 25, our loop starts from 2, it checks for 2, it again checks for 3, 4, 5, and when I becomes 5, this condition becomes true because 25 is divisible by 5 and it immediately returns false. So the output of this input is going to be false. So far, so clear. Great. Now let's talk about the time complexity of this function. So first, find how many iterations we are having in this function. So how many iterations are there? We are simply running a loop from 2 to n minus 1. How? See, we are ignoring 1 here and we are ignoring n here because we are running loop from 2 to less than n. So how many iterations will be there? From 2 to n minus 1, we have n minus 2 iterations, right? And sometimes we may have only one iteration also. Let's say if I pass n is equal to 4, then in first iteration, it checks if 4 is divisible by 2 or not, and it is divisible by 4. So we immediately return that 4 is not a prime number. So in case of 4, we are only running loop once. So we can say that sometimes it may take constant amount of time, and in some cases, it may take n minus 2 amount of time. So here we can use our friend big O notation to say that the upper bound of this function is going to be big O of n. Clear? So now if I ask you, can we make this code better? I mean, can we optimize this code? Don't you think that we are simply wasting so many iterations? Okay, let's see some observations. So we have some observation to made. So if you see any number and you find the divisor of this number, then you can simply observe that the divisors are always appear in pair. It means in case of 20, the divisors of 20 are 1 and 20, 2 and 10, and 4 and 5. And in case of 30, the divisors of 30 is 1 and 30, 2 and 15, 3 and 10, and 5 and 16. And when we multiply this, we get the same number. It means 1 into 20 is 20, 2 into 20 is 20, 4 into 5 is 20. In case of 30, 1 into 30 is 30, 2 into 15 is 30, 3 into 10 is 30, and 5 into 6 is also 30. So let's do some calculation and we'll see what comes out to be. So let's say we have a pair x and y, right? So we say that 1 is x and 2 is y. And if you multiply both the number, we get n, right? Simply if we multiply 1 into 20, we get n. So far so clear. Now if you observe all the divisors, you will see that one number is always smaller than other number. Here 1 is smaller, here 2 is smaller, here 4 is smaller. Here also 1 is smaller, 2 is smaller, 3 is smaller, and 5 is smaller. And if you see that if you multiply this number with itself, it means 1 into 1, that is also smaller than 20. So 1 into 1 is going to be less than 20. 2 into 2 is 4, and that is also less than 20. 4 into 4 is 16, that is also less than 20. So we can say that if you multiply x by x, we simply get a number that is less than n. Okay. So now after solving this, we get x is less than equal to square root of n. So what does it mean? It means in a pair, we are having one number that is always smaller than or equal to square root of n. Correct? So the square root of 20 is somewhere around 4.5 something, and if we get a floor of it, we get 4. So you can observe that 1 into 1 is less than 4, 2 into 2 is less than equal to 4, and 4 is equal to 4, right? And similarly it happens in case of 30 also. Okay, so now we can say that if x is less than equal to square root of n, then definitely y is greater than square root of n, and we can observe it that the square root of n is square root of 20 is 4, then the second number is greater than 4. Here also second number is greater than 4, and here also is greater than 4, so on and so forth. So we simply conclude that in previous solution we are simply iterating from number 2 to n. Now in this case we do not need to iterate from 2 to n. We can simply iterate from 2 to square root of n, and in between 2 to square root of n we simply going to find one factor of a number, and we found the factor, then we simply declare that okay, this number is not a prime number. So the idea is simple. Instead of running a loop from 2 to n, we are simply running a loop from 2 to square root of n. Now let's see our second implementation, and this is little bit optimized than the previous one. Okay, so what I have done here, I have simply replaced the value of n with the square root of n. So here instead of running a loop from 2 to n, we are simply running a loop from 2 to square root of n. So let's see what advantage we get after doing this small change. So in case of 7, we took 7 in the previous example also. So here also I am taking 7, and the square root of 7 is 2. So this loop is going to run from 2 to square root of n, right? So in case of I, 7 is not divisible by I, so the loop continues, and when I become 3, it simply checks 3 is less than equal to 2, and this condition becomes false, and our function returns true, right? So if you compare the number of iteration with the previous example, here we are running loop 1, 2, 3, 4, 5 times, and in our second implementation we are running loop only 2 times. So this is going to be a significant improvement to our isPrime function, right? Now let's talk about the time complexity of this function. Now instead of iterating from 2 to n, we are simply iterating from 2 to square root of n. It means the number of iteration we are making here is square root of n. So the time complexity of this function comes out to be big O of square root of n. So far so clear. Now I think it still has room for improvement. We can still optimize this function a bit. So let's see how we do it. So again we have some observation to be made. So in our previous example, we took small numbers like n equal to 7 and n equal to 25 and so on. So if number is small, then we don't have any problem. We have to iterate from 2 to square root of n. But imagine if what happens if n becomes larger and larger. Let's say in our case 809 is very large number and the square root of n is also 28. To find that 809 is prime number or not, so we have to run our loop from 2 to square root of n, that is 28. So we have to run the loop 28 times. So here we can observe some pattern and we can reduce the iteration significantly. So what is the idea here? So first of all, I am considering here if n is equal to 1, then we simply return false. And this is what we are doing so far. Now if n becomes 2 and 3, we simply return true. Why? Because 2 and 3 both are prime numbers. So I am assuming this. After this assumption, we can see that we are left with 4, 5 and so on numbers. Okay. So if you look at these numbers carefully, you can observe that if a number is divisible by 4, then definitely this number is divisible by 2, right? And if a number is divisible by 6, then obviously this number is divisible by 2, because 6 is also a multiple of 2 and 4 is also a multiple of 2. And if you see the number 9, if 9 is divisible by 3, then obviously it is divisible by 3, correct? So it means number 6, number 4 and number 9 is a composite number, because 6 is formed by the multiplication of 2 and 3 and 9 is formed by the multiplication of 3 into 3. It means 6 and 9 both are composite numbers. Same with 10, 12, 14. So after assuming this both the condition that n equal to 1 we return false, n equal to 2 and 3 we return true. So we start with the 4. So we can check that if the number is divisible by 2 or not. Let's move on to 6. So 6 is also divisible by 2. It is not a prime number, and so on and so forth. So we can cancel out all these numbers. We do not need to check for all these numbers. 10, 12, 14, 16, 18, 20, 22, 24, 26 and 28. Now we have cancelled out all the multiples of 2. Now it's time to check multiples of 3. So 3 is a prime number, right? So let's check multiple of 3. 9 is a multiple of 3. So it is a composite number. It means we do not need to check for 9. 3 4s are 12 is already gone. 3 5s are 15. It is also not a prime number. 3 7s are 21. 21 is also not a prime number. 24 is also gone. And 27 is also a multiple of 3. So you can see that how many iterations we are saving. So we don't need to check for 4, 6, 8, 9, 10, 12, 14, 15, 16, 18, 20, 21, 22, 24, 26, 27 and 28. So we are saving a lot of iteration. Now the next thing is we simply ignoring these 3 values and we start with this value now. And we start with the 5 and we can jump to the next number, and next number is going to be 5 plus 2, that is 7. So we simply check for 5 and then we check for 7. If number is divisible by both the number, then we can say that this is not a prime number. Then after 7 we simply jump, and after 7 we simply jump to 11, that is 5 plus 6. 5 plus 6. So we are simply jumping 6 steps at once. And we check for 11 and then again we check for 13. And after 13 we simply jump 6 steps ahead. So 11 plus 6 is going to be 17. So we then check 17 and then we check for 19 as well. So this is the simple idea. And using this idea we can save so many iterations. So let's move to implementation. So this is going to be our third implementation. And what we are doing in this implementation, we are simply checking if n is equal to 1, return false, because 1 is not a prime number. And then we are checking if n is equal to 2 or n is equal to 3, because 2 and 3 both are prime numbers. So we simply return true. And then in third if statement, we are checking if a number is divisible by 2 or if a number is divisible by 3. If a number is divisible by 2 and 3, we simply return false. It means it is a composite number and it is never going to be a prime number. So return we are simply returning false. After that, we are running a loop from 5 till square root of n, and in each iteration we are jumping 6 steps ahead. So we are starting with 5 and then we are going 5 plus 6, and in each iteration we are checking if n is divisible by I or n is divisible by I plus 2. As I shown you in example, we are starting with 5, we are checking for 5 and 5 plus 2, and then we are simply jumping 6 steps ahead to reach 11. Okay, so this is how our function runs, and at the last we simply return true if we are not able to find any divisors. So let's say the value of n is really large. In our case it is 289 and the square root of 289 is 17. So our loop starts from 5, and in case of 5 we are not able to find any divisor. We check for 5 and we check for 5 plus 2, 7. We are not able to find any divisor. So we move on to the next iteration, and in next iteration our I becomes 11. So we check for 11 and check for 13. So with both the number 289 is not divisible, so we move to next iteration. In the next iteration our I becomes 17, and this time 289 is divisible by 17. So we can say that 289 is not a prime number and our output will be false. Now in case of n equal to 409, the square root of 409 is 20. Our loop starts with 5, it checks for 5 and 7. Then in next iteration it checks for 11 and 13. Then in next iteration it checks for 17 and 19. In next iteration our I becomes 23, and that is not less than equal to 20. So our loop gets terminated here, and after the last statement is going to be executed, that is return true. It means 409 is a prime number and the output of this function is going to be true. So let's talk about the time complexity of this function. So after this modification, how many iterations we are having in this loop? Still we can say that our loop is having square root of n iteration, but it is much faster than the previous implementation, because we are putting one condition here for 2 and 3 and we are jumping 6 steps ahead in each iteration. So we can say that this implementation is much faster than previous implementation. So the time complexity, we can say that it is also a upper bound, and upper bound is represented as big O of square root of n. Great. So if you are still watching this video, then I have one bonus tip for you. So the generalized formula to find the prime number is given as 6n minus 1 and 6n plus 1. So let's put n equal to 1, we get 5 and 7 and both are prime numbers. If we put n equal to 2, we get 11 and 13 and both are also prime numbers. Okay, so this is it for this video. Thanks for watching. See you in the next video.